So we have learned LDA and QDA. Here I wanted to mention that when the dimension is high, so in a high dimensional setting for classification problem, I don't recommend either. And the reason is when P is large, estimating a covariance, P by P covariance matrix, and also actually use it, you have to invert that matrix. That procedure, and you're just going to generate a lot of error, and also it's very easy to overfit your problem, your classification problem. So you can actually show that when P is really large, and we believe some of them are noise features, the LDA can end up overfitting the data. We can show that when P is really large, LDA will eventually behave like random guessing. For binary problem, that means your classification error is just 50%. And so to address that issue, there are some remedies. One type of remedy is just to add some L1 penalty in our optimization problem. When we estimate the covariance matrices or its inverse or the mean vectors, just to require them to be sparse. There are some work along that line, but I don't want to review them here due to the reason I will mention at the end of this lecture. Another type of regularization is just to force the density function, a p-dimensional density function, to be independent. In that case, for example, if they are Gaussian, meaning your sigma matrix is going to be diagonal. And that type of work is known as naive Bayes. So what is a naive Bayes? Remember, for multi-class classification problem, the optimal decision rule is based on this discriminant function or decision function, which is pi k times fk. Here, fk stands for the density function for a p-dimensional vector x. So here on the left, this x is in boldface, is just x1, x2 until xp. It has p elements. And on the right, we basically factorize, we require that joint distribution function can be factorized as individual one-dimensional distribution function over those p elements. You can sort of view independence as a regularization for a high-dimensional problem. Then we're just going to estimate this one-dimensional distribution function for every dimension and for every class. And for example, if x is a discrete feature, then we just use histogram. And if x is a numerical feature, we can use kernel density and function because it's just a one-dimensional problem. That's often known as a non-parametric naive Bayes. Or we can just use a one-dimensional normal density function to estimate each one of those f sub kj. And that's often known as the parametric naive Bayes. For example, if we use a parametric Bayes, a naive Bayes, how many parameters we need to estimate in our training stage, meaning how many parameters we need to describe the distribution of x for the case class. Well, we need p means because each dimension is going to have their own mean. And we also have p variances because each dimension is going to have their own variance parameters. So here's a summary of the algorithm for parametric naive Bayes. In our training stage, we get our n training samples, xi is p-dimensional, and yi takes categorical variables 1 to k. And our output will be pi, which is k by 1 probability vector, or mixing vector. And our mu, which are the mean for p dimension and for each k classes. So we can arrange our mu as a k by 1 matrix. We also need to estimate sigma square for each k and each j, so we can arrange our sigma square also as a k by p matrix. Then how we form prediction for a new test point x star, we basically going to compute the following this decision or discriminant function for each small k, and it is just -2 log of of this mix and weight and times the product of those one-dimensional normal density functions. and it can be simplified this way. Here I want to point out some subtle issue. When you get this equality here, we basically take log, and you can see for each of the normal density function, we can get the first term is a half log sigma square, and the second term is exponential. We can just get the quadratic term in the exponential component. You're going to find out in some of those naive Bayes packages in R, they compute this term as log, and then they call a command in R called dnorm, which basically evaluate this normal density function and then take log. And sometimes you're going to find out this may not agree with your calculation here, simply because sometimes if your x star is very far away from the center, so you could have you have to evaluate something like log e to the power, let's say minus 30. But because e to the power minus 30 is just such a small number in the calculation, and are actually going to give you some are actually going to treat this part probably just as e to the power 18. So you're going to give you some number like, log like minus 18. But if you directly evaluate this quadratic term, you may exactly get minus 30. But if you evaluate the density function and take log, you may get something like minus 18. So there could be some discrepancy between your own code, if you're going to code your own naive Bayes, versus the one from some of the R packages. So here I illustrate this problem using the naive command from this kernel and LAR, like KLAR package. I use this spam data. So spam data is a built-in data set for elements of statistical learning package. It is a binary classification problem indicating an email is a spam or not a spam, and the feature will be some kind of a characteristic of the email, and basically the frequency of some of those special words. And you can load the data, and then you just call naive Bayes. And you're going to get some warning messages, and the reason is, R tries to tell you that there's some probability of very close to 1. Then you can go through my R code page. So eventually you're going to find out why you get this error message, and then you will see how I implement my own naive Bayes calculation, and then how my calculation is different from the R output for the 20 observation. And the reason is just what I said before, because for that particular observation, the number in the exponential component is very small in terms of the magnitude, very large in terms of the magnitude. So there's some discrepancy in terms of you calculate log of the density versus you directly evaluate the expression of this log. So just want you to be aware. I don't know whether you're going to same issue with Python. So here's a quick summary of what we've discussed this week for discriminant analysis. So in discriminant analysis, we estimate the first we actually find out the optimal decision rule for classification is based on this purple conditional probability. But how discriminant analysis approach this problem, how discriminant analysis get this purple? Discriminant analysis starts to estimate the joint by going through a different factorization where we estimate the margin of y and then estimate the conditional of x given y, and we put them together, we get the joint, and then we can just get the marginal from the joint. And depending on how we model the conditional of x given y, we have discussed, several DA methods like QDA, LDA, or naive Bayes. I think the discriminant analysis is really conceptually simple and works out well for some low-dimensional problem, especially for QDA and LDA. They usually work well for some of the low-dimensional problems, but it is not an effective way of building classifiers. And so naive Bayes, let me talk about naive Bayes later. So first, let's look at LDA. Why I don't think LDA is not an effective way. So let's consider binary LDA. So the K can only take two different values. And this is our discriminant function or decision function. So it's a linear function of x plus some numbers depending on sigma, mu, k, and pi k. Because it's a binary classification problem, and we only care about the magnitude of dk for k is equal to 1 versus 2. So what matters is the difference of this d1x minus d2x. And so you can find out that difference is really it's just a linear function of x. All we care is this p-dimensional coefficient vector beta and this constant and this intercept beta 0. Meaning for LDA, what's really relevant is just a p-dimensional parameters, which is not surprising because it's a linear function. So it just needs an intercept and need a p-dimensional coefficient vector. But how we estimate this p plus 1 parameters? We estimate it by a much larger collection of parameters. We estimate a p by p covariance matrix sigma. We estimate p-dimensional, two p-dimensional vector mu1, mu2, and also a mixing weight pi 1. So it is not effective in the sense that we estimate a lot of parameters, but all we need is sort of a low-dimensional representation of them. So in the next couple of weeks, we're going to discuss how to directly just learn this purple and conditional probability. For example, in logistic regression or tree model, we just directly learn this probability, or we directly learn the decision boundary, like in SVM. So back to those three methods, QDA, LDA, and naive Bayes. I definitely would not recommend QDA unless your P is really small and you do have enough data and it's large. LDA may work out well. So in some problem, if the P is not so large, you do want to take into consideration of some of the correlations among the features. So if that's the case, go with LDA. Naive Bayes, because we have that independence assumption, so we don't model the correlation among x's. It's surprisingly, naive Bayes works out well for some problems, but you still could get overfitting with naive Bayes. If you look at the naive Bayes formula, you can look at our decision function, and basically we get our first term is just something related with mixing weight, and then we sum over the contribution for each of the p dimension, how we contribute sort of every bracket, the quantity inside the bracket is the evidence we collected for the j's dimension for supporting x star and being from the case like from class K. If in cases if your dimension p is really large and you believe a lot of them are noise, then you accumulating your evidence, you may accumulate a lot of noise and contributions that actually will dilute your evidence. So I would suggest when you do naive Bayes and you have your p-dimensional feature, when you want to apply naive Bayes, I would recommend do some variable screening, like two sample t-test, and only keep those dimensions that are significant among the two sample t-test if we're talking about binary classification. And then you drop some of the features, then apply naive Bayes, and in some applications it can work out very well.